Good day, everyone, to the Kontur roundtable for the selection of a better pavement rehabilitation strategy by using non-destructive testing data. My name is Mike Heitzman. I'll be the moderator for this 1-hour roundtable. And Kent Martin, the marketing director for Kontur, was the one that put everything together. So if you are having troubles, it'll probably be Kent that'll be responding to you in the chat box during the course of the presentation. And I'm going to go to, I think I'll leave it right there actually. Hopefully everyone can see my screen, and that will be essentially the method by which we work forward with the agenda and today's topics. So at this point, I'm going to move into essentially a slide on the agenda itself. And we'll talk about today in this next hour. First is an introduction, and then we will talk about some 11 problems that agencies typically have with their pavement rehabilitations. It's probably not an all-inclusive list. From that, then, we selected about 6 state agencies to vote on how those top 11 or how those 11 problems stack up as to what are their priorities. And from that, we gained 3 top problems. And the panelists today are going to give some perspectives on how those top 3 problems can be addressed with non-destructive testing. And if everything works well and we stay on task, about the last 10 minutes of the hour or so, we will go to an audience questions and answers with the panel, a little bit of a dialogue there. So as we go through the presentation, if you do have a question that you'd like to pose to the panel, feel free to put that into the chat box so that that can be picked up by Paul and or Kent, and we'll get to that in the last 10 minutes, unless there's something very urgent that they jump in during one of the particular sessions. So as an introduction to this topic, as a highway engineer myself, the latter parts of my career, probably about the 2/3 of my career actually, one of the biggest things we struggle with is whether we have got the right pavement that we're going to do a rehabilitation on, and that we're going to do that rehabilitation at the right time. And further, we have to make sure we're going to apply the right rehabilitation. And I have plenty of stories in my mind as to times when we did not, in fact, get the right treatment, and we did not do it at the right time. We certainly had plenty of pavements to choose from. But getting that right pavement at the right time and the right treatment is always important. And it's important because every time we go out to do a roadway inspection for rehabilitation, we run into all kinds of things. In the particular slide here, it's pretty obvious that the left lane and the right lane are not the same, and we would probably not want to treat them the same. But what are we going to do? Depending upon where we're at, we probably have differences in climate that come into play. We certainly have differences in traffic levels. And in fact, knowing a little bit about this project, that right lane has heavy loaded trucks coming out of the quarry, and the left lane is the light trucks coming back into the quarry for more aggregate. So there's an obvious reason why the damage in these 2 lanes is different. We also have differences from one agency to another. So it's very important that we recognize that there are differences in how we approach design and how we approach rehabilitation. Having said that, then, we move into how do we determine the problem and how do we actually address it? It would be nice if we had this non-destructive testing data to essentially look at the entire pavement, not just a couple of spots, in order to do a better job of determining the best solution for the rehabilitation. With that in mind, we can always go to a visual inspection, and sometimes you have more eyes than you have visual pavement to look at. And I'm sure with this particular group, if we were to poll them for a solution, we'd probably have as many different solutions as we have feet on the ground. So certainly visual inspection is important, but we also have to do typically we do some types of point investigation. Coring is very common for most agencies. It's fairly simple to do, but we are certainly learning that it's more and more difficult to be able to get out on the pavements to actually do any type of coring because the levels of traffic are getting much greater. So with that, here then of course on the right side there was a DFT to try to get some strengths underneath, but still we're only dealing with one particular point. So with that in mind, if we look at non-destructive testing considerations, the amount of moisture in the pavement can be very critical to whether we're going to find something, particularly with ground penetrating radar. Winter de-icing chemicals can also play havoc with ground penetrating radar. Certain soils are going to give us problems, and certainly they don't all behave the same. And depending upon what type of distress the pavement is actually does have, whether or not we can actually detect it may determine what type of non-destructive technology will be best suited for that. And something that was certainly a very important part of the SHARP program was to try to do the non-destructive testing at speeds that would be matched with the traffic so that we could essentially keep the interference to the traffic to a minimum. So with that, we then came up with this list of potential pavement problems. And water in the subgrade, block drainage systems, delamination between asphalt layers, stripping in asphalt layers, which some might call some very severe types of delamination. But delamination in this case is more just a debonding between layers. We do have stripping in the transverse cracks, certainly in the upper Midwest, where you have the freeze-thaw cycles through the winter. Rutting, concrete slab steel alignment, concrete slab faulting. These are all different problems that we have in the system. Thickness of the concrete cover over the rebar generally is not a problem, but it can be a problem from time to time. And what is the thickness of the asphalt layer so that they can place a bonded concrete overlay? So these 11 items were then posed to 6 state agencies to give us a list of what they consider to be their top problems. And keep in mind that certainly the problems will vary with the level of traffic in that state, the climate in that state, and other things such as materials. But from those 6 surveyed agencies, the 3 top situations which come up to play was thickness of the asphalt, what is the source of rutting, and what is the water in the subgrade. Now, my own personal suspicions are the original proposal or the original query was, do you need to know the thickness of the asphalt for in-place recycling? But based on my experience with working with agencies, a lot of them simply need the thickness of the asphalt no matter what they're going to do, because they may not have the rigorous database on which to determine what that asphalt thickness is. Water in the subgrade, when I was teaching at the graduate level, I told the students the first 3 problems with any type of pavement are water, water, and water. And I think most of us would agree that water in the subgrade is very critical. And we'll talk about rutting as well. So those are the 3 topics we're going to talk about during this roundtable. And with that, I'm going to allow our roundtable panel members to introduce themselves, and we can go on from there. So Bill, if you would, please introduce yourself to the rest of the group.
Great. Thank you, Mike. I'm Bill Owen. I'm chief of the geophysics branch at the California Department of Transportation. We have over 20 years experience working with ground penetrating radar applications. We've been working with Kontur back when they were 3D radars starting in about 2015. And so we've been using ground penetrating radar and the 3D radar through the Kontur system for our pavement applications, both for asphalt thickness, for bridge decks, for pavement problems, including voids and water in the subgrade, as Mike has identified. We've also used it for utility locations. So we have a very broad-based approach for GPR applications here in California.
Ken, would you like to introduce yourself? Ken, you're muted. If you unmute.
All right, thank you. Yeah. So I'm a senior principal with Infrasense. We've been working with the 3D radar system since the Sharp 2 project, where I was a co-PI back in 2010, I think. And we've been doing all the applications that Bill just mentioned, thickness, stripping, other things, continuously, a lot more over the last few years. We also have a couple of research projects focused on 3D radar. One to automate the detection, the presence of and misalignment of dowel and tie bars in concrete, and another to automate the detection of stripping in asphalt. So that's what's going on there.
Thank you, Ken. Nate, would you like to introduce yourself, please?
Yes, I'm Nate Bech. I'm a project engineer with ARRB Systems. We are a user of 3D radar contour sensors, but we don't actually do any of the data processing ourselves. We have one unit on our iPave data collection vehicle, which is like a comprehensive pavement assessment vehicle. It does GPR, but also structural integrity and other types of distress. So I'm primarily responsible for managing and processing the data collected by that vehicle.
Great, thank you. Martin, we saved the best for last.
Thank you very much. Yeah, it says here I'm a senior road specialist. I would maybe introduce myself as a road nerd. I have 25 years in the industry and has been working with I still call you 3D radar from time to time, actually, since the beginning in the first workshop in Trondheim. But I've been working, actually gone all the way through most of the NDT technologies. Start out with road profilers, have like 20 years with the GPR, and work from day to day as a road specialist and doing these type of analysis that we're talking about. And for the last 4 or 5 years, I've been in charge of our Raptor project, the traffic speed deflectometer device that we run in Ramboll. So yeah, it will be a great time today, and I've spent quite some years interpreting the GPR data, so hopefully we can have some insights on that.
Very good, thank you. And with that, for the audience, keep in mind that you have these panel members who have got the experience with using non-destructive testing technologies. And as we go through our 3 particular scenarios of the problems we have with our pavements, feel free to put together a question or a comment that we can talk about later during the roundtable. With that, let's move right on to the first of the pavement problems. And the first one is the thickness of the asphalt layer for in-place recycling. And we generally take cores, but certainly we need to know a little bit more about the thickness. I've had plenty of projects where the thickness of the asphalt was not the same across the pavement, or it wasn't the same as what was in the database. So there are issues here as well. And with that, Bill, I'd like you to start with some comments about how NDT would be used with determining thickness of the asphalt layer. Bill, you're muted.
Always. Thank you. We've been involved in a number of projects that use where we're looking for thickness of asphalt layers. Although the focus of this presentation is on the thickness of asphalt layers for in-place recycling. We've used it for bonded concrete overlays. We've used it for looking for problems or for confirming network level construction. And so for in-place recycling, it's become a very popular alternative for construction or repair of asphalt pavements, primarily because it has a number of benefits in terms of both cost and time, and also in preservation and conservation of natural resources. So in terms of cost, time, and materials, you generally achieve about 50% savings over the cost of doing a from scratch construction. So it's a very popular alternative. And in terms of the types of recycling that are available, that includes a offsite cold replacement or cold in-place recycling. Hot in-place recycling as well. So there are a number of different types, even including like full depth reclamation, where you can take out either a portion of your asphalt pavement, leave a portion of the original pavement behind, grind up the over surface, add new binder to it, recompact it, and after that you get about another 20-30 years of lifespan out of that new pavement. So again, it's a very popular alternative. And for ground penetrating radar applications, we typically are using that to, one, confirm the pavement construction at these projects. That's especially important when we're doing a partial cold in-place recycling of a composite pavement where we have, say, a asphalt overlay over concrete. So typically we'll have anywhere from 4 to 6 inches of asphalt over concrete, and that's a very popular treatment for the interstate part of the state highway network in California. And so making sure that they actually have enough asphalt pavement to achieve their mill design thickness is very important. And so radar applications are pretty critical for that. And for other applications such as full depth recycling, our engineers like to know what are the estimates of available volume of pavement that they can get from the milling operation. So we've been involved in running radar on a number of quite large projects. Probably the largest one we've done consisted of 110 miles of continuous recording of 3D radar data using the Kontur system, where basically we started out and did a loop down one interstate and came back went southbound on Interstate 5, turned around and came up northbound on State Route 99. There are two roads that are parallel to each other, separated by about 10-20 miles, and we simply turned the unit on, recorded data, and spent about 2 more months trying to interpret everything and provide estimates of thicknesses to our pavement engineers for their design. So that was really extremely beneficial. I mean, there isn't any other type of technology that would have been able to do that, where we basically could go out and collect data for an hour and a half, 2 hours, and collect 110 miles of data, and then go back into the office, process all of that, and produce a rather large file to our pavement engineers, giving them a report every recording interval of pavement thickness for their design application. So it's been very useful for us for trying to solve this particular problem.
Thank you, Bill. Ken, do you have, I'm sure you've worked with a lot of states. What do you have to share on the thicknesses?
So yeah, I think Bill's covered the application to recycling pretty well. Just a little bit of background. Measuring thickness was an application that was developed back in the 1990s with traditional single antenna GPR and has sort of migrated up with many applications and now with 3D GPR. One of the applications that we've been getting more involved with is using the thickness data in conjunction with deflection data to calculate pavement properties and predict remaining life. So, for example, Nate from ARRB told you he has a Kontur system attached to their traffic speed deflectometer. So this system is now collecting data on hundreds of miles of roadway, and we're able to analyze that data for layer thickness, combine that thickness data with the deflection data that comes from the TSD, and use that information to calculate effective structural number, subgrade modulus, and then, with traffic projections, predict remaining life. So that has sort of two dimensions of application. One is sort of on a network level. You can go through hundreds of miles and identify the sub-segments that are deficient and what needs to be needed, as you say, where these are the places where the pavement is weak. We don't have to worry about those other places. But because there's so much detailed data available for those segments in need, we can even go further and recommend what a treatment would be. And I want to point out an application in Mississippi where there was a 13-mile section and the state was planning to do full depth reclamation on the entire section. And by using the GPR data to estimate the structural properties, and plus doing some stripping analysis with the 3D GPR, we're able to show that the full depth reclamation was only required in a portion of the project, and the rest of it could have just have been cold in place recycling, and they saved about $15 million on that project. So just this simple measurement, it has quite a bit of benefit.
Very good. Thank you, Ken. Nate, do you have something to add? Ken gave you an introduction there.
Yeah.
Yeah, thank you, Ken. Yeah, as just users, we collect, ARRB collects a lot of GPR data, but we don't process it. And the reason we collect it is basically because of thickness, trying to determine thicknesses of existing pavements. We added the 3D GPR to the iPave because people were asking for it. Our customers were asking for it. And primarily it was to get layer thicknesses as part of sort of the full, package for, design applications. Just generally, you need to know the structural condition of the pavement, which would come from the traffic speed deflection, the deflection device, and then the thickness of the pavement. So we were getting just the deflection, but not the thickness. So the thickness, maybe not exactly for in-place recycling, but thickness is definitely the main reason that we are using this technology.
Great, thank you. Martin, do you have anything to add from the other three panelists?
Yeah, I have some ventures out of the topic maybe, but it's like both Ken and Nate said that. I mean, this is a crucial part for what I call structural information on pavements. So this is a standard product. I'd say hopefully it will be a standard product in the market worldwide. But right now we have 5 systems, GPR systems serving just the Nordics. So I think in my part of the world, at least, this is a standard product to use. So just discussing here, roughly we collect somewhere around maybe 10,000 kilometers, 15,000 kilometers a year of GPR data, and it serves a really important purpose. I have some, actually, regarding the in-place recycling, we've done some quite interesting projects. We can see a larger and larger need for this type of data in what we in the Nordics call mill and fill operations. So it's not only a question of the in-place recycling, but also correcting the design of the road, the crossfall and things like that. Then it's very crucial to know both the total thickness of the asphalt to calculate the bearing capacity, to know how much can you take away in some places and add in others, but also for the in-place recycling, of course. So we've done some quite large projects on this, even on airports, where we correct the camber of the or the crossfall of the runway. And when we move into the airports, we can see a real benefit because we operate both with the 2D and the 3D GPR. But here we can see the true strength of using a 3D system, because not only can we see the total thickness, but it's possible to detect the delamination of the asphalt way better than with any other product. And especially on the airfields, when we have the problems with the de-icing materials, we can see the deterioration of the asphalt way better with the 3D system. But it's like we say, it's usually combined with other NDTs to make a complete picture. But not only, since this is a Kontur webinar, I always say I wouldn't do without the GPR because it plays a crucial part in the puzzle.
Great, thank you. That was a good discussion of the thickness of the asphalt layer, and certainly it has a lot of different applications relevant to our pavements, no matter where we're at. I want to move on to the next topic, which is the water in the subgrade. And the pictures here are from a project I was working on. There was water bleeding out of the project, out of the pavement days after a rainfall. And after we got into the exploration and cut a trench into the shoulder, it was quite obvious that the water wasn't necessarily sitting up in the asphalt. It was down below in the subgrade, and then it was bleeding out along the shoulder. So with that as a brief introduction, Ken, have you had a lot of projects where moisture is one of the main problems you're having to deal with, and how does the non-destructive testing technologies help you there?
Yeah, no, thanks, Mike. So yeah, moisture, well, GPR, everybody knows, is very sensitive to moisture. So if it's there in any quantity, it should show up. We typically look at the layer interface amplitudes, and in the base or the subgrade, the amplitude of the reflection at the top of that layer will be significantly higher than in the surrounding areas if the moisture, because the dielectric constant of the material will go up with moisture. We had a project on an interstate where there was a lot of rutting going on underneath the right wheel path about a year after it was rehabbed, and there was some suspicion that there was a drainage problem, but it wasn't clear exactly where and how much. And using GPR, we were able to do two things. One is we found that the drainage line, which was supposed to be offset into the shoulder, was actually offset into the wheel path because there was some alignment problem during construction. So the trucks were kind of just beating up this drainage line, and eventually fell apart and clogged. So that was the cause. And the question is, well, how extensive is this problem? So we're able to use GPR, map the amplitude of the reflection from the boundary between the base and subgrade, and calibrate that to local in-place moisture contents to be able to essentially plot the moisture of the base and then identify the zone where this was a problem. And that really kind of narrowed down the area that had to be repaired. So yeah, this is a common request to look for areas of high moisture. The method we use, as I say, is looking for, in Examiner, we can output the amplitude of any interface, and we look for areas where the dielectric or the reflection amplitude is sort of significantly above the background.
Great, thank you, Ken. Bill, can you share a little bit from the west side of the country?
Yeah, sure. We've done very similar applications that Ken's just discussed. Nothing as extreme as the example that he's presented here, but we've used 3D radar systems and Kontur system for looking at problems with our pavements that are related to water in the subgrade, and particularly the benefits that we've seen from it is one of the advantages in California is we have a Mediterranean climate, so that we have a dry period, seasonal dryness, and then we have wet periods in the wintertime. So we can really use the Kontur system and the radar, not just the Kontur 3D radar, but even single channel radar systems for looking at changes with seasonal variability, particularly after rainfall events. And some of our most successful projects that have involved looking for pavement defects, both in asphalt pavements and in concrete pavements, has been related to basically looking at acquiring radar data immediately after rainfall events, and looking for where the water has migrated within the pavement section, and that's the changes in the amplitudes that we see related to moisture infiltration has been very successful in identifying voids, identifying delaminations, and identifying problems with stripping in our pavement sections. So it's been very useful on a project level basis for looking at those specific focus types of problems.
Great, thank you. Martin, do you have anything to add?
Yeah, I think, I mean, it's like you said, my lecturer also told me that water is the three top problems. I think that goes all around the world, actually. So we've done some interesting projects on this. This is, of course, the most defining thing for a road specialist to look into, especially defining areas where you have a potential problem with this. So we've done some really, because, I mean, looking at the dielectric values from the GPR, it is very sensitive to the water, but also sensitive to the type of soils in the substructure. So we've actually combined the GPR with information from the soil maps, where we did an automated extraction of the soil material information. So we extracted, it was a combination of deflection data from the Raptor, and then we took from the GPR the dielectric values and the amplitudes and the variations, and we ran those towards the information that we got from the soil maps, and we did this on a larger scale. So it was not only project based, because then you can of course move in an area with the same type of soil structure. And we could find some really good correlations and informations. And what actually we were looking for is the areas where the deflections and the dielectric values were more than normally off from what you could expect, because those are the areas where you most likely have the problems with the clogged drainages and low points and stuff like that. So that was a pretty interesting application. I think there's actually more to do within that field. It was just a small test we did, but it showed some really promising results that we're going to dive deeper into. And then, since we're talking, I mean, water in the subgrade, water usually when we talk about it in the road application, it's in the fluid state. But of course, in the colder climate areas of the world, we have the problem where the water turns to ice, and that can be a huge problem as well, especially in the Nordics, of course. But I have an example of last year when we took the Kontur system to Antarctica, and we're actually trying to find ice lenses in a structure down there. So that's another application where you can actually look for the frozen type, which you can do in any part of the world, of course. But it just shows how versatile a system like this is, where you can actually, if you know how the system works and what's possible to pull from it, you can adjust it and tweak it to solve any type of problem you have. So those are two things. Otherwise, for water in the subgrade, I mean, this is the GPR is the best there is on the market for finding variations in the water content. But I always say that the one who finds a foolproof system of determining the actual content of water, that will be a rich man for the future, I'd say.
Very good, thank you. Nate, would you like to close out this particular topic with any experience that you have?
Sure. Well, I've never, as far as I can recall, we have not collected GPR data specifically to look for water in the subgrade, but we collect GPR data for everything. So I am certain that there are many sections that have had this problem. We just haven't, or I'm not aware of them being done for that specific purpose. The nice part, though, is you can just go back and look at it. And it's also because we collect it with all this other information as well, like pictures. Like I spend a lot of time looking through just images of roads, and like that top right-hand image, you can see clearly there's a water problem underneath the pavement. If I saw that, I would suspect that I know what's happening there, but the GPR, I could just go back and confirm it, and I might not have to do what's shown in the bottom picture.
Very good, thank you. And I know with the traffic speed deflectometers, you could potentially have a same thickness of pavement, but suddenly have some higher deflections, and it's most likely, at least in my experience, that you'll probably find some water down in that subgrade if you have those higher deflections. So
yeah,
it is,
it's
go ahead.
sorry. Yes, it's all sort of complementary. The different types of information we collect just sort of inform one another, but the GPR is one of the most valuable.
Right, very good, very good. All right, so the next topic, the last of our three topics, I wanted to start with a little story of my own. I was driving to a vacation spot, and in the middle of the night, I'm driving along the freeway, and this variable message sign shows up. And if you see this sequence of variable message signs and you're the DOT, the agency that has this roadway, you know you have a very serious problem. And in general, we do consider rutting to be a serious problem because of the safety implications. When it does rain, you do end up with essentially a source or a location where the water is going to pond, which happens to also be the wheel path, and can certainly increase the potential for the hydroplaning.
Yeah.
So the third of our top problems is the source of rutting. And I thought maybe Martin could start on this particular topic and discuss any experience he's had with trying to use non-destructive testing technologies to determine where that rutting is coming from.
Yeah, no, I mean, this is what I've spent the last 25 years of my life doing. And especially, I mean, what we think about directly when we see the source of rutting or rutting in general is, of course, the road profilers, where we can detect the how large the rut is. We have for, I'd say, before GPR really entered the market as a commodity product. We did a lot of investigations on trying to describe the curvature of the rutting and the width of the rut to determine some source of the depth of the problem. What if it was a narrow rut or a wide rut, and how far down into the construction the problem we're laying. And then, since the falling weights are pretty slow operational, it was quite limited use. It was more a project-based. It wasn't possible to use it on the network level. But since we've moved into the realm of high-speed collection of deflection data, I'd say the source of rutting now, and that was the natural combination with the GPR as well. So this is kind of like a three-step program. You need the profilers to determine it's a very quick and non-destructive way of defining the differences. But then with the deflections combined with the GPR, we have a way better way of determining where in the construction our problem lies, especially if it's like in the asphalt, or if it's in the subgrade or even further down. So I'd say sometimes I get asked the question, should we do GPR or should we do something else instead. And I always say that's the dumbest question I've heard, because it's the combination of things that makes the magic happen. We're trying to solve a puzzle, and no one would try to do that with half of the pieces. We need the full picture. So it is a combination of the surface data, the structural data, which we get from the deflections and the GPR. So it's kind of like creating the trifecta we need to solve this problem.
Great, thank you. Nate, would you like to add something on this particular topic?
No, actually, Martin just explained in much more detail than I could exactly what I was going to say. So
I stole your thunder, sorry.
exactly. That's okay. But yeah, we have the same philosophy, which is why we have, well, transverse profiling equipment, deflection equipment, and GPR all in the same vehicle. That's why, because you need to have really all three to figure out what is the actual source of rutting.
Very good, thank you. Ken, how about you? Do you have some projects or at least one experience you might want to share?
So yeah, our experience with this indicates that the 3D radar array is uniquely it has a unique capability for this type of application, because in principle, and I say principle, and I'm going to elaborate, you can measure the variation in asphalt thickness across the width of a pavement. And if there's a variation in thickness, you could associate that with rutting in the asphalt versus rutting in the base. But you can't really just assume a dielectric and measure the thickness, because it turns out that the wheel paths are densified somewhat, and their dielectrics are different, and you may get a misleading conclusion. So you have to calibrate the equipment with metal plate reflections to be able to calculate the dielectric and the time, and then you get an accurate measure of the profile of the thickness. And with that, you can determine, is it thinner under the wheel path, so the rutting is in the asphalt, or is the asphalt uniform and the base is thinner rutting in the base? That's my view on this.
Great, thank you, Ken. Bill, do you have some experience with issues of rutting?
We have not been using any radar applications for rutting problems, but we have been using it for general subsidence issues. So anywhere where we have some overall pavement subsidence that has been identified, we've been called in to assist in looking for the source of it. We have a number of really good examples of it. Actually, I can. If you're interested, I can share my screen. I can pull up my presentations from, I think we did this roundtable a little over a year ago, where we had great examples of source of subsidence in pavement. So I can go ahead and grab my screen. And let's see what I can do here. I'll grab screen 2 and I'll share that. And so you can see that screen right now?
We can see the screen.
Okay, great. So this was a particular problem. We had pavement subsidence identified. We went out and ran the Kontur system, identified an area of where they had visible pavement distress and subsidence. And at the base, this was a concrete pavement. So at the base of the concrete, we found very good high amplitude reflections, evidence of pavement distress, evidence of a defect. And then when we went out and actually had follow-up coring done, they discovered that there was essentially everywhere where they drilled out in that area, they found a void. So this was a great confirmation of how radar can be used for these types of applications, for looking for, source of rutting, source of pavement subsidence, where there are problems with pavement that can occur. So we were very pleased with that particular result. So I'll just keep showing this example for the rest of my career. It's such a great one.
Very good, thank you. Let's see if I can share that screen again. Whoops. Where are we at here? There we are. All right, so back to our roundtable discussion. We have talked about the 3 top problems that some agencies have indicated would be there. We started with the thickness of the pavement, and we went into moisture being a big issue, and ended with rutting. And yes, I've had some experiences where I've had to cut a trench across an interstate to find where the rutting was at, and I would sure have liked to have just had the non-destructive testing ground penetrating radar rather than me laying in a trench with the crash worthy cone between me and the traffic going next to me. So there are issues like that. So we have in fact completed the 3 topics that we wanted to share with the audience. And Kent or Paul, do you have any comments from the audience that we need to share with the panel?
Thanks, Mike. There is one question actually regarding Bill and Caltrans' capability. From an anonymous source, so I don't know who posted it, but Bill, just about having in-house capability or outsourcing, and what those capabilities are that you have in-house.
Mm-hmm. Yeah, certainly. We actually do have in-house capacity. So we have the Kontur system, and we do this work in-house. My group actually goes out and we acquire and process this 3D radar data. So we have the capability to provide that service internally. We've also subbed out this work based on workload demands and based on timing and scheduling. Actually, Ken's group has actually gone out and done work for State of California and California Department of Transportation as well. So we use a mix of both in-house and contractor capacity to meet workload demand.
Thanks, Bill.
Ken, you might have a little bit to say about that as well. You work with a number of states.
Yeah, we work as, our business is a service provider. So a lot of the data that gets collected by Nate's group comes to us for analysis. There's a section of interstate that somebody has to do a project on. So we'll get Nate will upload the 3D radar files. We'll get the traffic speed deflectometer files, and we'll run that as a project. So we get data from Nate, we get data from other sources, and we have our own data collected with both ground coupled and air coupled systems.
Great, thank you. Martin, you working from the European side of things? I think Martin's still there.
Yeah, I'm here.
Okay. What's the experience in Europe as far as in-house non-destructive testing capabilities versus consultants?
Yeah, we have a bit of another situation here, at least in the Nordics. There's quite low capacity on the governmental side, but there is definitely a quite good capacity on the service provider side. So I think we have a long history here of using the GPR, again, with having Kontur as our next door neighbor. It's quite a lot has happened in this market here. So no, yeah, as I said before, we run 5 systems just serving the Nordics. For us, this is a go-to method that we use in like all applications, especially on the interpretation side as well. We produce large scale projects as well, like for 20,000 kilometers and more, collecting high capacity network volumes. But this is what's so good with the data, and just to kind of like summarize, and I think you said it best in the end of the water problem here, as trying to use the data to avoid doing the every now and then you have to do your coring. We have a coring device as well, so we do quite a lot of them. But I always say that's the last resort. And if we should do coring, you should always use this type of data to pinpoint the places where you get the most value out of that data, because there's a risk for the people who are doing it and to the other traffic, and of course a high cost per point. So you want the very best bang for the buck for every coring you do. And I say it's a crime not to use the NDT data to determine where you get that effect of the disturbances when you do the destructive testing.
Very good, thank you. And I know I've had a project that had a problem with rutting, in fact, but project was 20 miles long and all I had was a core every half a mile. That was the technology I had available to me at the time. Paul, do we have any other comments or questions from the audience?
Yes, just one about the surveying on ice, actually, which is an interesting topic, one that I don't have much experience, application experience of. In fact, I've seen examples of it, but never done it myself. So it's kind of interesting. What about what amplitudes would look like, or if there's any examples of this type of ice surveying?
Martin, I think you're the chief
Yeah,
expert here in the panel.
I kind of threw that one at myself. No, yeah, it's a different type of analysis you do, and that depends on, again, not being biased here, but if you have a frequency-based or a time-based type of system, because with the frequency in the frequency domain, you can do so much more trying to detect this and not going way too much into the details, because then you can analyze the data in a couple of different ways to detect this type of anomalies. But otherwise, it's also, I mean, frozen ice and water have completely different properties in sense of the GPR. And I mean, on a situation like Antarctica, or I've done the same on Svalbard and other places, it's actually quite strange, because you're operating in the upside down world, because usually we tend to operate on roads that normally are unfrozen and then freeze in the winter time. But when you operate in the Antarctic and Arctic areas, you actually operate in an area where the road defreezes during the summertime. So in terms of deflections and everything, you have to think completely the opposite. But I think, again, there's not that many people operating in this. So I maybe that's even a topic for a future webinar. I think we can dive down to that.
Very good. Yeah, I'm not sure we'd have much of the audience from Florida or Georgia or Texas, but certainly I have heard and had some discussions on that. Ken, you've worked with some of the northern states. Do you have anything that you've done with the ice issue?
So we've had an interesting experience where we were doing a pavement thickness project in New Hampshire in March, and it had been quite cold prior to the collection of the data. And we were just measuring asphalt thickness on an interstate. We had a great deal of difficulty seeing the bottom of the asphalt. And it was because, as we later learned when we repeated the survey a month later, was that the base was frozen. And frozen base has a dielectric of about 4 or 5, which is very similar to the dielectric of asphalt. Once the ice melted, we had normal base, the bottom of the asphalt showed up very clearly. So don't do thickness surveys when the base is frozen.
Bill, do you have much problem at all, like maybe in some of the mountain ranges with ice during surveys?
We have yet to actually ever have to do any kind of applications on that. Of course, so we have in our mountain regions, we have our freeze thaw cycles in the winter time. Generally, it's not so cold that we have to worry about freezing in the subgrade or freezing in the pavement itself. It generally stays warm enough that we don't generally worry about it. But there's that would be an interesting problem if one actually popped up. We'd love to see something like that.
There you go. Well, if you have to get through one of your mountain passes, that might be a reason why you have a problem with the survey.
Yep.
Paul, do you have any other questions from the audience?
No, we have one hand raised. I just want to see if there's a mistake or whether
Yeah.
or not.
In fact, I just Dave, if you want to unmute yourself, you can ask the question there.
Yeah.
Yep.
Nope. Okay, we will
I
move
guess
on.
not.
Other than that, no more questions.
Well, very good. We have a few minutes left. Any of the panel members want to do a 30-minute, 30-minute. How about a 30-second closure from your perspective?
Yeah,
Bill, you
certainly. I
wanna
guess I can
start?
start. So, give my little 30-second speech. I think we got involved with Kontur as part of the Strategic Highway Research Program, and we've just basically found that since we brought the system on board and started using it, we found that it's been invaluable for really helping us out on some pretty complex pavement problems, and it's been a very successful application on our side. We've seen a lot of increased use, a lot of expansion on it, and we've had a lot of variable applications, not just in addressing these 3 pavement problems, but in addressing a lot of other general problems. And we've got very good feedback from our client base, our users, if you will, and we've been very happy with the system and how it's performed.
Great, thank you. Ken.
Sure. Yeah. I think it's important to recognize that the array setup of the 3D radar system has some unique capabilities that don't exist for single and dual antenna systems, particularly for issues that are spread out laterally across the pavement as well as longitudinally. For example, dowel bars. You can image dowel bars very clearly. You can see them, bing, bing, bing. And depending on the speed of data collection, and you can get a lot of detail. You can see if they're misaligned. You'd never be able to do that with a single or dual channel system. Stripping as well is something that occurs over an area, not a line. So layer thickness, not so much, but these other applications, 3D radar the array system is invaluable for detecting these conditions.
Great, thank you. Nate, do you have anything to close with?
Yeah, thank you. I just wanted to say that we're very happy using the Kontur antenna with our vehicle. We found that we have kind of a unique situation about how we have it set up on the vehicle, because it's like underneath the tractor trailer, but it's worked great. It integrates well. And working with Ken, we've been able to collect a lot of interesting data for a lot of different people. If we're ever collecting data for you, don't feel shy about asking for us to maybe change the GPR settings for specific applications, or letting us know if there's something you're interested in looking at. We can always do that because it's on there. It's going to be on anyway. So
Great, thank you. Martin, we'll let you wrap up the panel.
Kind of like the same as the others. Like we said, we've been using the 3D radar for quite some time, actually since the beginning. And we both operate a couple of 2D radars as well. So I can say that historically, we've tended to move more and more to the 3D, and especially like with the information on the lateral side, and that it's so easy to combine multiple measurements to one single SWOT. And looking at the industry, I can see that Kontur is the developments that's happening on the software side, on the usability, is actually the main reason of driving that change. So I can see more and more customers being really happy with moving. I mean, I've been working with geophysicists applications for a long time. So for me, it's second nature. But for most of our clients, they have no idea what I'm talking about when I'm starting to show them the radargrams and whatnot. They want the result. And I think that's the major change, that it allows me to actually move a little bit away. It's not in my nature, but I'm trying to move away from the techie stuff and actually focus on delivering worth to the customer. And Examiner helps me with that. So yeah, a bit of praise in the end, but you're worth it. So
Very good. Thank you. Well,
Hey,
we've come to the, yes.
Mike, we do have a couple of last questions that are pretty interesting for the panel. One from Roman. Thank you for a very interesting report. Tell me what data processing tasks are already being solved using artificial intelligence. How about finding boundaries? So if the panel wants to opine about any of that,
Yes.
Ken?
Yeah, so we've actually begun to develop an AI system for layer tracking. We basically teach it with projects we've done in the past, how we've tracked it layers manually, how they've the tracking has been confirmed with cores. The user can pick the projects he wants to do the teaching, because there's a lot of different kinds of projects. You don't want to teach use concrete pavement to teach asphalt picking, whatever. But the user can pick the learning set, and then it will automatically track the layers for the new data. It's still in the development phase, but we see that coming along in the near future.
Excellent. Anyone else want to jump in on that?
Well, I think it's interesting that there's been some comparisons between what we understand currently with machine learning and the original old school empirical or algorithmic types of layer boundary detection. And some of the results coming out of that has indicated that basically machine learning doesn't really provide much more benefit than the standard approaches. So it's interesting to see where that goes and how that fleshes out, and if there's going to be any additional progress made on that front. But it was interesting to see some of those results come out.
Yeah.
And, sometimes the old school methods work great.
Yeah, Bill, I think I will add to that. And what Ken might be pursuing is when you start working in an agency and you're doing network level analysis and not project level analysis, just the mountains of data that are being collected, the more we can automate the analysis, I think the better off we are for getting network level data.
Right.
Oh, certainly. Yeah. Automation is going to be the key to really making the 3D radar applications cost effective. The problem we're going to always run into is that there's always going to have to be a human eye put on there and some kind of review on it to make sure, and one of the biggest problems, the biggest drawbacks of machine learning is that, geophysics has often been criticized as being a black box. And, a lot of people will point out that machine learning is kind of the ultimate black box. I mean, you're putting an answer in and you have no idea how the answer is being derived. It's just you're getting an answer and you're making an assumption that this is going to be great and it's going to be right. So are we there yet? I don't know. I mean, Ken's work is not necessarily doing that for boundary detection. I mean, he's doing some stuff that I think is going to have some real good applications for machine learning, because they're very, very strong boundaries, and they're very it's more of a tractable problem than some of the boundary detection issues that we run against. But it'll be interesting to see how it all fleshes out. I mean, I'm not being critical of it. I'm not against it, but we just need to be more kind of realistic in our expectations of it, and kind of see how the technology develops.
Nate or Martin, do you have anything you want to add to the artificial intelligence topic?
No.
well, I actually, I have something in the realm, because I mean, when we're talking about more on the automation, because we are also trying around a little bit with the machine learning, but these are all terms that kind of like get mixed up in the industry. So I just concur with what Ken and Bill said, but on the automation side, I think there's actually more to do, because it's like we should put the human resources on the things that matter. And we can see that there are actually quite some things that can be automated, taking away the boring parts. We did one project with 1,600 bridges with a 3D with the Kontur system. Then, of course, if you add that up, it's a lot of hours spent creating projects and clicking around and doing stuff like that. And then we did some really amazing automation work. So the people working with it actually spend their time making the proper decision and not just shoveling data around. So there's many sides of that automation machine learning coin.
Right.
Kent, you have
Yeah.
another topic then?
Our last question, I know we're getting close on time here, from Jack Morris Rowe, sorry. Question for Nate. When collecting large quantities of GPR data on the TSD vehicle, what is your process for data management? Are you using external hard drives? And that's actually a great question that a lot of our customers have used different methods. So love to hear what you're doing, Nate.
The short answer is yes. We are using external hard drives. The antenna that we're using, we always have it set up to collect on all channels. So I believe it has 24 channels. So it's collecting, as Ken alluded to, the full width of the pavement, generates quite a lot of data. So we have that. We manage it primarily, yes, with hard drives. If we have to send it to somebody, we usually set up shared folders, things like that. I know when we work with Ken, we have just a shared folder. We can send him the files. If it's with other clients, we can send a hard drive.
Excellent.
Great.
Well, thank you very much, guys. One last thing from Kontur on the marketing side. Look over the summer. We'll be sending some emails out and advertising one of our new upcoming products that is getting released, which would be the dielectric mapping / density mapping. So we're going to have a couple of webinars on that, explaining and moving forward with it. So keep your eyes out for that. It should be very exciting for you pavement folks.
Good.
Very good.
Yeah.
Well, in closure, I want to thank the audience for listening in and providing some comments. Hopefully you gained a few little bits about the use of non-destructive testing technologies. I certainly want to thank the panel for taking their time to share your experience with the audience. And a copy of this roundtable will be sent out through Kontur, so you can look for that in the future, so you can have a permanent record of what we talked about. With that, Kent, I'll let you have the final word.
That's it. Appreciate you guys coming out. Hope everyone has a great summer. And thank you very much again for attending.
Take
Okay.
care.
Great.
Bye.
Thank
you.
you. It's been a pleasure.
Hi.
Thank you all.
Thank you.
Bye-bye.